Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, very grateful to James Lee for giving us this second installment in the description of Talagrand's theory of majorizing measures. Please.
All right. Thanks. Okay, so yeah, it feels less and less informal. This room is very formal, but okay. So let me recall what I talked about last time, and then we'll get started on some new stuff today. So I'm going to assume a little bit of familiarity with what I talked about. I'm not going to go over the definitions again, but well, maybe I will. I just won't write them down. So we had last time a Gaussian process. And if you weren't there, this is just a collection of jointly Gaussian random variables. So every linear combination of these variables again has a Gaussian distribution, every finite linear combination. And then we said what we were interested in, and we motivated it last time, was the expected supremum of all these random variables. And as I said last time, there's really no loss in assuming that this set T is finite. So you can assume T is finite all the time. This is just an expected maximum. So this is the quantity we were interested in. And let me just, today we're going to have to use more properties of Gaussian processes than we did the last time. But let me just say the only two things we used were, the last time was that, well, we assumed that all these random variables are centered. Okay, so in general, when I say Gaussian process, I always mean a centered Gaussian process. And this is the last line I'm going to write here, so I hope it's still visible. And we used the sort of some kind of tail bound for Gaussian. So okay, so before I write this, let me add one more thing that we had last time. Whenever we have such a process, there's a canonical distance that this process carries, which is the following, which is just the L2 distance on the set of random variables. So the square root of the expectation of xs minus xt squared. Okay, so given this distance, we can write sort of the classical concentration inequality. The probability that xs minus xt is bigger than lambda is at most e to the minus lambda squared over twice the distance between s and t. And again, just the distance between s and t, of course, it's just the variance of xs minus xt. Okay, so that's the setup. And then what we did last time, we said, well, how can we control this quantity in terms of the geometry of the process? So what I mean by the geometry of the process is that we have this process, we have this distance, which this now makes t comma d into a metric space. And now we can look at the geometry of this metric space and see how the geometry affects this value. And what we did last time was the following. So we said, OK, suppose we have a bunch of subsets, t0, inside t1, inside t2, all sitting inside t. And they're going to satisfy the following bound. I guess the size of t naught is 1. And for t bigger than 0, or for the n bigger than 0, the size of t sub n is at most 2 to the 2 to the n. So I'll say what these were for. I'll remind you in a second. But if we have sets satisfying these conditions, then we can use these sets actually to get a bound on this process as follows. So this is a result of Fernique. Again, this is not how Fernique stated it, but it follows from Talagrand's work, which is that the expected supremum of this process is at most this quantity. Okay. Is at most, okay, and this is, of course, this. All right, so in general, when I write a less than or equal to squiggly b, so a less than or equal to squiggly b means a is at most some constant times b, and this constant should be something universal, so it doesn't depend on any of the parameters involved. Okay, so this is at most 10 times this, where 10 is some constant. Okay. Okay, so this is what we proved, and the way to think about this was basically as follows. T0 is set on one point. So let's say that little t0 is the one point in big T0. And then you can think about constructing a tree where at the next level of the tree we have T1. And then at the next level of the tree we have all the points of T2 and so on. And then how did we prove, how would you prove this theorem? Well, we just said, OK, so these are, all the edges of the tree here represent, the endpoints are pairs of points in a metric space, so the edges have lengths on them. The edges of the tree have lengths on them. And if you look at what this quantity is, this quantity just looks at basically the longest path in this tree, but where the nth level is weighted by 2 to the n over 2. Okay? And if you want to get an upper bound to match that, all you do is you come here, you look at the number of edges sort of look at the nth level of the tree. How many edges are there in this level? Well, there are at most 2 to the n times 2 to the n plus 1 edges in the nth level, because there are there are most 2 to the n points here, and at most 2 to the n plus 1 points here. So that's at most like 2 to the n plus 2. Okay. And then if we apply this concentration inequality, what we get is that we can take a union bound over sort of all the edges. By the way, if you didn't see the last talk, this is not necessarily going to make sense. It's just a refresher. I assume that people saw the last one. But basically, if we take a union bound over all these edges, we can be certain that if we have sort of xs minus xt here, then xs minus xt is at most 2 to the n over 2 times its length. So we take a union bound saying that sort of none of these edges is stretched by more than 2 to the n over 2. And well, if you look at the probability of being bigger than lambda times your distance, and this is the number of events, then you see that putting 2 to the n over 2 is exactly 2 to the n over 2 is about square root log the number of edges in this level. So the probability that some edge is bigger than this, we can take a union bound and we can get this sort of that none of these edges has value xs minus xt, which is bigger than its length times 2 to the n over 2. Okay? So in any case, we had these sets. We took a union bound down the tree, and this is what we proved. This bound of Fernic. Okay? Which is a very nice bound. Yeah, go ahead.
What if this capital T is only one element, so all the b's are 0? I don't understand.
Capital T is only one element.
Yeah. What happens?
Then
Yeah, but the right-hand side is 0.
And so is the expected maximum. So
The expected maximum?
of a center random variable is 0, right?
Oh, right.
Yeah. So in fact, we get the right bound, even for when there's only one point. All right. So good. It's good to check special cases. Okay. So. So then now what we want to do, is we got a pretty good upper bound. We'd like to consider lower bounds on this quantity. Okay. And in fact, I said what the lower bound we're going to prove is last time, but let me just restate it in a second, which is going to, in a way that's going to be useful for what happens later. So let me restate this upper bound in a slightly different way, as follows. Instead of thinking about subsets, let's think about, this pen is awful, so I'm not going to use it. Let's think about a sequence of, this is a sequence of partitions of T. And it's such that it satisfies two properties. The first property is that it's a sort of a nested sequence of partitions. So A sub j plus 1 is a refinement of A sub j for j bigger than or equal to 0. And the second property is that these partitions we're taking a sequence of partitions into each one into some bounded number of pieces, and as the index increases, they become we get more and more pieces. So they become more and more refined. So my claim is that we can restate this bound in the form, I guess I should introduce one piece of notation. So I'll use this a lot. So for a partition P of the set T, and some point in T, point little t and t, let P of t be the unique set that contains little t. Okay, so in a general, I have a partition. I'm just asking what set contains little t. It's going to be P of t. I claim that we can rewrite this bound now in the following way: expected sup t xt. Not rewriting it, but in fact, just a consequence of it is at most this quantity, which we'll see in a second. So the same thing, sum sup over all t's 2 to the n over 2. But now here we'll just look at the diameter of this set a sub n of t. Okay. So this upper bound is going to be a little bit easier to work with. I mean, to sort of this sort of upper bounding mechanism. To see that this works, just notice that if you give me any such sequence of partitions, then from the set a sub n, I'll give you a set t sub n. So this set has at most 2 to the 2 to the n points. I'll give you a set t sub n. What do I do? Just take 1 point from every piece in the partition. Okay? And then you can just check that that this quantity is upper bounded by this quantity, because the distance from any point to t sub n is at most the diameter of the piece that contains it. So well, we know this is an upper bound, so I claim that this is an upper bound on this. There's an upper bound on this. All right. But this is going to be a little bit easier to work with. All right. So this is the upper bound. And now the immediate question that arises, or maybe one that arises after you stare at it for a while, is how good of an upper bound this is. Okay? And in fact, so after Fernique proved this upper bound, again in a different form than this, using the language of measures instead of the language of partitions, he started thinking about trying to prove that there are processes where sort of this is not the right way to control the expected supremum. And apparently he thought about it for about 10 years. At some point during that time, became convinced that there must be that this is sort of not the best way to upper bound this quantity. And actually started asking Talagrand to work on sort of more and more complicated examples, trying to prove that sometimes you could do much better than this upper bound. Okay, and sort of as the story goes, every time sort of he would give Talagrand some hairy example, eventually Talagrand would come back and say, no, actually there's a sequence of partitions, or there's a majorizing measure which gives a good upper bound, until one day Talagrand thought to himself, well, why don't I try to prove that in fact this upper bound is great and is the only way to upper bound the expected supremum. And then, as he told me a couple of weeks ago, 2 days later he proved his sort of majorizing measures theorem, which says that I'll state it now. So it says that basically this is the only way to upper bound the expected supremum of a Gaussian process, by choosing these partitions and then looking at this value. So for every Gaussian process like this, there exists partitions a sub n satisfying 1 and 2 over here, such that this holds. So diameter a sub n of t. So it just holds. And now, I mean, I'll state it this way. I could put the sup here, but let me just state it this way because it's a little bit clearer. We say that every sequence of partitions gives us an upper bound on the expected supremum. So Talagrand proved that actually, given any process, there exists a sequence of partitions such that this is also a lower bound up to a constant. And this has, I mean, the sort of the strength here. I mean, we can put, maybe I'll put it so it matches here. Such that this is also a lower bound. Okay, so and in particular, this showed sort of this shows, if you remember what I talked about last time. Okay, I understand why you've all staring at me in a strange way. As we talked last time, this actually, for instance, characterizes sample continuity of Gaussian processes, for instance. You can say that, well, you can sort of say exactly what geometric condition has to be satisfied for a Gaussian process to have this sort of sample continuity property we talked about last time. Okay, so now I want to focus on this. Okay, so basically, how can we construct really good partitions of this space? Every partition gives us an upper bound. Now I want to construct one somehow that matches its upper bound. And to do that, we're going to have to use more than just these two properties of Gaussian processes. And so we'll go through the properties now and we'll prove them. It's really interesting if you want to think about extending this theory to things that are not Gaussian processes, because both of these are fairly lightweight. I mean, like you feel like, sort of process, like families of random variables with sub-Gaussian tails are all over the place. You could hope that you could prove, and in fact you can prove this kind of upper bound for all these families. But the lower bound requires, or at least is believed to require, much stronger properties of Gaussian processes. So let's talk about what they are. Okay. So the first thing we want to do is, if people remember what we use this. Okay. The first thing we need to do is find. I mean, this we proved an upper bound. We're trying to prove a matching lower bound. We need to have some. We want to have something which kind of sort of matches the behavior of this upper bound in a fairly strong way. So if you were in the talk last time, the sort of the test case for the analysis of this union bound and what we would get if we applied it to many points instead of just one was we took a bunch of we thought about taking a bunch of random variables that were sort of uniformly spread out. So let me just draw a picture of what I mean. So we said, look, if we have a bunch of random variables, and now look at this metric on them, and suppose the distance between all of them is about some quantity alpha. So for every pair of them, the distance is about alpha. We said, OK, look at this inequality, take a union bound. So suppose we have m points here. Then the union bound says that the expected supremum in this case for these m points, maybe we'll write it this way, for these m points is going to be about, well, we can prove an upper bound, which is something like alpha times square root log m. Right? All the distances are alpha, so if we look at one pair, then the probability that they're bigger than some c times alpha grows like e to the minus c squared. So we should choose c to be about square root log m if we want to take a union bound over m squared pairs. Right? So, OK, so this was sort of the motivating case, basically, for handling one level of this tree. The last time, we need to prove some kind of bound. I mean, as a first step, we'd like to be able to say, well, this bound is tight. In the simple case where our process is just sort of a bunch of random variables that are all uniformly spread out. So that's what we're going to concentrate on first, just proving that we can match this upper bound for this simple sub kind of process. Okay? And so, well, this is actually a classical inequality, so called the Sudakov inequality, which says this. So let's take here a Gaussian process, and let's suppose we have some uniform lower bound on all the distances, such that distance st is at least alpha for all distinct pairs in T. Then, well, we'd like to prove this lower bound. So we'd like to prove that the expected supremum is at least alpha square root log the size of T. Okay? So and it's not going to be equal, or we're going to lose a constant. Okay? So if we're going to try to prove a matching lower bound, this seems like the first thing that we should try to do. Try to prove a lower bound in this case, where I just give you some uniform lower bound on all the distances. So I say xs minus xt has some definite amount of variance. Can we prove that the expected maximum has to be really big? And sort of as the number of points grows, we get some growth that matches what the tail bound gives us. OK, so this is our first goal. It's actually not so, I mean, it seems almost, I mean, you can think about it. It seems almost like it should be very easy. you might start thinking about how to prove it. Okay, it's not so easy, but at least we can imagine one very easy case of this, which is if the Gaussians are just stall independent. Okay, and this is not just an example. We're going to reduce eventually to the independent case. But let's look at something even simpler. Let's just consider G1, G2 up to Gm to be IID sort of standard Gaussians, IID normal 0, 1 random variables. Then I will leave it as an exercise to see that in this case, the expected maximum G1, G2 up to G sub m grows like square root log m. Okay? I'll leave it as an exercise. It's just the fact that, right, the tail really does behave in some, there is really e minus c times t squared probability mass past t. So the probability that one of them is bigger than square root log m, if you put the right constant, is at least say, is at least say 1 over m. So, or 1 over square root m if you like. So if you have m of them, one of them should get there, okay? Because they're independent.
Can you do a second moment?
You mean you want to count the expected number they get out there and then?
Calculate the expected number to calculate the second moment.
Interesting question. Even so, the answer is I don't think so.
If you know the distance, what can you say about the probability that both variables in between both variables are large? Do you have that information?
Certainly. I mean, in the case when you just have two, you can just write down exactly what they are. You can just write down the projection of one on the other. But it is not going to be enough. So, well, we can. Maybe I'll think about it while I'm talking and come back to it. I don't think it's enough to use the second moments here. I mean, it is enough to use second moments. I just think not with the second moment method. We'll have to use sort of slightly more delicate.
Replace method by some other way.
Nonetheless, the lemma we'll present has some independent value, but what's the problem? Okay, let's not. We don't have that much time. Let's not get wrapped up in it at the moment. Okay. So we're going to use this, and then another classical fact called Slepian's lemma, which is the following. So let's take two Gaussian processes on the same index at t. All right, I'm making this up now. GP is going to be Gaussian processes, such that one of them has distances bigger than the other. So this is always bigger than y sub s minus y sub t squared for all points in our set. Okay? Then the claim is that, and again, the claim seems fairly intuitive, but then the claim is that the expected sup of the xt's is bigger than the expected sup of the yt's. Okay? So if all the distances here are bigger than all the distances here, then the same thing is true of the expected supremum. This is, and we'll prove this in a second. Let's just see that we can reduce it to that given this lemma, we can reduce Pseudocal's inequality to the independent case. Okay? So the way we'll do that is, let me write here, maybe not, I'll move over. Well, what we'll do is we'll just map all the x's to independent random variables and make sure that all the distances go down. So just send okay, so I have xt, what should yt be? So yt will just be basically alpha square root 2 times g sub t, where this is a family of IID normal 0, 1, just IID standard Gaussians. I'm proving that with this lemma, we can reduce pseudo-Gaussian inequality to this elementary calculation. Okay? So this lemma involves two families of random variables in the same index set. So you give me your xt's, here are the yt's. They're just alpha over square root 2 times a bunch of IID Gaussians. Now you can check that, I mean, the distance here is exactly, the distance between any two here is exactly alpha. And by assumption, over here, the distance between any two guys is at least alpha. So we definitely satisfy the fact that all distances have gone down. Therefore, therefore the conclusion holds. So what does the conclusion say? Well, the conclusion says that the expected supremum of the xt's is at least the expected supremum of the yt's. But now this is exactly equal to alpha over square root 2 times the expected supremum of the g sub t's. And we already said that an elementary calculation gives us this. Okay? So if we can prove Slepian's lemma, then we've proven the Sudakov inequality. That, again, and which sort of at least matches the upper bound when we're in the uniform case. Okay. So now to prove Slepian's lemma. All right. And it's a very, all right, I'm going to erase this. Hopefully everyone got it. If not, apparently it's being recorded. But let me keep Sudakov's inequality around.
So in general, the pairwise, I think you said this before, but do they determine the expected supremum?
So the covariances, the values, so since this is centered, these values for over all pairs of points in the set, these actually determine the entire process. So the process is determined by these, not just the supremum, the process itself, the random variables are determined by these values. So if you want to translate, they're determined exactly by the distances up to a translation. Okay, so what's that? Sorry, yeah. So they're up by a mean zero Gaussian. So in other words, if I look at the process xt or the process xt plus z, where z is a mean zero Gaussian, these two processes have the same distance, even though they might have, well, they will if. Yeah, they'll have different covariances. Okay, but this actually won't affect the expected supremum because the expected value of z is 0. So, okay. So now we're going to do maybe the first non-trivial thing that's happened, including last time, which is proving this inequality. I like the proof, so that's why I'm presenting it. Also, it's useful. I mean, this is informal, so we can prove everything we want to. All right. So how does the proof go? So it's going to go like this. So first of all, I'm going to assume t is finite. T, obviously, we're only using it for the finite case. But if you prove this for finite t, you can just check that it immediately follows for arbitrary index sets t. So let's consider two processes, x1 up to xn. And y equals y1 up to yn. And let's recall our assumption that, yeah, yes, good call. All right. And let's just rewrite our assumption in a slightly different form. OK, so I'm going to almost prove this in full generality. So here's the assumption I'm going to make. I'm going to make the assumption that, let's make sure I go the right direction here, that expected value of yij is at least the expected value of xi xj for all I and j. Okay, that's certainly well. Okay, and I'm going to assume that expected value xi squared equals expected value yi squared for all I. Okay, so certainly this is a weak. Now, if given both these conditions, it's weaker than this. Okay, so this implies what's written in red, because this condition combined with this condition and gives you this condition. It's only slightly weaker. Yeah. What's that?
What implies what again?
If this theorem.
This theorem implies that.
So let's say it this way. This condition is so this condition implies this condition. Therefore, well, the theorem could go the other way. That's how. Yeah, but this condition implies this condition. But I'm going to make this assumption. So I'm not going to prove this in complete generality. By the way, the same argument I just gave with a small tweak, you can use this assumption to prove it. Just instead of writing y sub t equals write this, and then add some, and then add some. Okay, I don't know what the add some beta z. Okay, beta depends on t. To all the variables, where z is just some other IID normal 0, 1, and then go, and then you can basically you could ignore all this stuff and do the same, and then reduction to the standard Gaussians is the same because this is all independent. But and then I mean you can choose beta so that you have this condition being satisfied. But don't worry about that. I'm going to use these conditions, which are slightly stronger than these conditions, just for ease of what's going on. Okay, so. And now let f just be some function from Rn to R. Okay, this is the whole thing. You should think about. Well, I'm not sure what you should think about. You should think about f being well, let f be some arbitrary function, and then what we're going to do is the following. Let's define. We're starting with x, and we want to compare x to y. So what we're going to do is we're going to define some kind of continuous interpolation between the two processes, right? So let's define x of. Okay, so this is annoying but I thought about it. It's really the right thing to do. T now is going to denote a real number between 0 and 1, but it's time over here also classically, but it's going to denote actually a time. But it's okay because the indexes here are now i's and j's, so you won't be confused. So everything that's written in red, the indexes are i's and j's, and think of t as a time. We could replace t by something else like epsilon, but then epsilon doesn't seem like a time, and then so. Okay. All right. So think about this process, which at time 0 is x, and at time 1 is y. And we'll move between x and y. And then we're going to try to see how this thing, some quantity we care about evolves as we move from x to y. Think about f as the quantity we care about. Okay? And then let's finally define phi of t to be the expected value of f applied to x, applied to this process at time t. Okay? So this is we have some value we care about. Let's look at its expected value when we the expected value, f of this thing at time t. And if this is phi of t, what we're going to try to show, and I haven't given any conditions on f yet, we'll try to show that that phi of 0 is at most phi of 1. And that will imply that the expected value of f on x is at most the expected value of f on y. Because at time 0, this thing is x, and at time 1, this thing is y. Okay? So now it's clear what we should do. We should analyze the derivative of this thing with respect to t and see how f is changing. So let's do that.
It's going to be increasing.
Yeah, so we'd like to show that the derivative of this thing is always non-negative, and that will give us this. Okay, just in case you're wondering, if f was really the maximum, we would be proving this inequality in the wrong way. F is just going to be the indicator. We're going to prove something stronger. F is actually going to be the indicator on some product of sets. So F is just going to be an indicator of a set in Rn. And we're going to prove that the probability of, let's make sure we're going the right way, the probability of y being inside some set is bigger than the probability of x being inside some set. And therefore, the probability of x being outside of that set is bigger than the probability of y being outside of that set, which will give us something like this. But for now, you can just look at everything in red and see what's going on. All right, so now let's hope that I remember how to do calculus. So let's take the derivative and see what happens. All right, so here's what happens. Okay. Well, we have to use the chain rule, right? So let me write it down, and then we'll see what's going on. F x t times x I prime of t. Okay. So the derivative at time t is you look at how much f is changing in the ith direction, and you multiply it by how much how much I is changing, how much the ith direction is changing. Okay, so that's the chain rule. Looks good. This is the directional derivative in direction I. Okay, so now we need to analyze this thing. Good. So now, basically, and what I wrote this is expectation, so there should be an expectation here. Okay. So now we're just going to be able to analyze this term by term. So let's just fix one term. So one term. So fix some I, and let's prove that actually this thing is not negative. All right. So how can we do that? Well, here's the main fact, which is cool and comes and is the we'll prove the fact. It's that if we look at the expected value of x, basically we want to look at how does the derivative in the ith direction correlate with what's going on in the jth direction. Okay, so we'll look at this thing. All right. Okay, so this is super. Now we have to just go back and so what is it? We get like so now I'm just taking the derivative of xi of t. It's just this simple expression. So we're going to get minus 1/2 1 minus t to the minus 1/2 xi, right? Plus 1/2 t to the minus 1/2 yi. That's the derivative. Okay, and then we're going to multiply times xj of t, which is just, let's maybe write it here, square root 1 minus t xj plus square root t yj. All right, and we're taking expectations. Okay, so first of all, we didn't say it explicitly, but look, this is nobody would ever say this, but I'm going to say it anyway. We can assume that these two processes are independent, right? There's no, we're never talking about them on the same side. So we assume that these two processes are independent processes, and then the point is that the cross terms here cancel. The x, y terms go away because they all mean 0, and we're just left with something which is great because this thing cancels out with this, and this thing cancels out with this, and we just get that this is half expected value yi yj minus xi xj, okay, which is greater than or equal to 0 by our assumption. So our assumption was made to guarantee that we had some so that these things were positively correlated. When we increase, I, somehow that should be positive and correlated with j. So what does it mean? Let's just write down what this means. This means we can write xj of t as some alpha j times xi prime of t plus z sub j, okay? Where z sub j is an independent Gaussian random variable. And the whole point is that the inner product is bigger than 0, and the alpha j's are non-negative. Okay? So this is my claim. If I give you, this is where you should really think about Gaussians in terms of Euclidean geometry again. Of course, we can write xj as its projection onto this random variable plus the orthogonal component z sub j. So this is orthogonal, which is the same thing as saying it's independent. Okay. Everybody cool? We can write this like this. Okay. So then to finish, let's finish over here. So now what we're going to do is, we need one more sort of argument. We're going to look at this quantity, okay? And sort of how does this quantity depend on the alpha sub j's?
One point you're going to make an assumption about f.
Yeah, I'll add another assumption about f here. I just want to see what it's going to be before we, Okay. Right. So we don't know anything about f. F could be arbitrary, so we haven't said anything. You're right. So I said try. So okay, we're trying right now. All right. So we write this like this, and now okay. So let's see what happens. So basically, I want to think about doing the following. We're thinking about this quantity as the alpha j's increase. Okay. So when the alpha j's are all equal to 0, all right, then maybe we'll just do the 0 case right here beside it. Then what we get is like expected value di f sort of some z of t. Z of t is just the vector of these zj's when all the alpha j's are 0 times xi prime of t. Okay? But now these z's are independent of these things. So the expectation, and that we can, it's the expectation is the product of the expectations, and the expectation of all these are 0, right? Because what are these? These are just, we wrote it down. These derivatives look like this, and these are both expectation 0. So the expectation of the derivative is 0. So the point is this is 0. Right? Again, so if all the alpha j's are 0, then this thing is equal to 0. And now what I want to happen is, as I raise the alpha j's, I want this quantity to increase, to never get smaller. And that, if we can prove that, then we prove this is bigger than or equal to 0, which proves that this is bigger than or equal to 0. Okay? So now you just say, well, what condition on f do I need so that when the alpha j's increase, this thing increases? And the condition you need on f, you can check, is just that that all the mixed second derivatives dijj are greater than or equal to 0. Because what does it mean? Okay, let's see what happens. So let's suppose that alpha j we know is positive. So So if this is, like, for instance, if this is negative, then if this is negative, then this is negative. So increasing alpha j makes x sub j go down, which by this fact makes this go down. So if this is negative, this goes down, which is does that make sense? So right, like increasing. Okay, I hope it makes sense. So we assume that dijf is bigger than or equal to 0. So if this is negative, then as alpha j goes up, this goes down. Okay, so this is negative, this is going down, which means that since the dijf is greater than or equal to, it means this is going down. But this is negative and this is going down, so this thing is going up. And if this is positive, then maybe I should have punted on the positive case first. If this is positive, then as the alpha j's increase, this increases. But now dijf is bigger than or equal to, so as this increases, and so they go up. So when when the alpha j's are equal to 0, this thing is 0. When they increase, this quantity increases. So we know that this quantity is greater than or equal to 0, and this thing is just a sum of these quantities. So we know this thing is greater than or equal to 0. All right. So that implies, maybe in sort of nonlinear board usage, that implies that phi t is greater than or equal to 0 for all times t, which implies that phi of 0 is at most phi of 1. Okay, so we've proved that sort of under all these assumptions, there is no try. How does it go? There's only do. There's no, I don't know what it is. What does anyone remember what Yoda says? Yeah, there's only do or do not. There's no try. Yeah, okay. All right. So we have this conclusion. So let's just use, okay, so now let's finish the proof of Slepian's lemma. By the way, this is useful in lots of other things. For instance, in you can use it to prove hypercontractive inequality. This is just a nice thing to interpolate between the two processes and then take derivatives. It's a beautiful kind of thing. So now to finish, we just need to choose our f. So what is f going to be?
Does it matter what you pick for x of t? Could you have chosen any other interpolation?
The nice thing here is that the 2 norm of the coefficients is 1. So could I have chosen the answer? Could you have chosen some other interpolation? Basically, the answer is no. What did we use for the interpolation? We used this great fact that the derivatives exactly canceled out and didn't depend on t. So basically, we chose the speed of the curve so that our derivative term wouldn't have any dependence on t in it. Not our derivative term, but our term that looked like this, xi prime t, xjt, sort of, we didn't have to do anything interesting because it had no dependence on t. It was exactly expressible in terms of this. So somehow this is, you could try to parameterize it by any speed you wanted. I think you would come up with this speed when you tried to work out the details. This is also the, I get the sense that this is also the, somehow, right. So somehow, I mean, like you can think of more complicated settings where you want to choose a path between these two random variables. And somehow this is all I know about. Everything Talagrand does in statistical physics involves choosing these paths carefully. That's what, I don't know if anybody. Anyway, so it's like a very simple case of like a very cool phenomenon where you interpolate from one Gaussian to another and see what happens. And you try to get some monotonicity on the way. OK, so we need to finish. So how do we finish? Well, just take F to be the indicator of a subset H. Here, A is a subset of Rn. And just take A to be the product of a bunch of half-lines. So I guess we should say capital N. So the half-lines look like, maybe I should, like this for any lambda i's you want. Like this. And then, OK, so first of all, you have to check that this condition holds. It holds trivially. As you move to the right, you tend to be, what happens as you move to the right? If you,
Don't we just smooth them out this edge? You can have that. Is it a pointwise inequality?
What, this? This is pointwise. So, but of course, it doesn't matter what happens at the boundary. So, in any case, if we apply it like this, then what we get is that, OK, so this is about, so if we apply it to this f, we get something about, we get that the y's being in this intersection have a greater probability than x's being in this intersection. That's what we get when we apply the theorem, which means if we restate it, it means that the probability, if we take the union of all the yi's being bigger than lambda I, so the question is some yi bigger than lambda I? Well, they have a higher probability of falling in the product, so this is, so falling outside the product, which is what this union is, should have a lower probability for the xi's. Okay, and this immediately implies that expected value of the sup of the xi's is bigger than the expected value of the sup of the y's. I equals 1 n. You agree?
Yeah, maybe you can still explain this derivatives.
Yeah, how do you take the derivative of a step function twice?
Are you going to smooth or?
No, I don't want to smooth. I mean, this is really like, I mean, OK, you know, yeah, I didn't even think about it because it's such a, you don't need to, you can take the derivative. The derivative is, I mean, yeah, you can smooth if you like, and then take a limit of the smoothings that converge to these sets. I'll leave it because I don't know how it's. So this is a standard. Sorry. So I mean.
But you can just then still explain intuitively or take in terms of right derivatives why you have the right sign.
Yes. Why is the sign correct? It's a good question.
This thing is usually 0. So.
I understood it a second ago. Well, OK, except at the one time that it's interesting. So, crap. Yeah. So somebody tell me if they see it before I say it, because I mean I had to do it earlier today, but then now I'm gonna have to like. So the function gets. Larger. As you go this way. Right, that's the right direction, right? You agree it's the right direction? So what's the reason that it holds? Why is it
just
there?
write formal derivatives as minus infinity on this boundary. Just write the first derivative and then take the second derivative.
You want to put the derivative as minus infinity?
Just on the just on this line, but then it stops being minus, then it starts being 0 again.
Right.
And it's 0 above. So now then if you take you differentiate horizontally now? Or
Yeah, this was horizontal. So now we should...
Now you differentiate vertically and you see that the thing goes from minus infinity on that line to 0 later. So this...
Yeah, so it's either, okay, so I mean you're either 0 all the time, or if you sit on this line, then eventually when you cross the other side as you go, so it's really, this is
the line goes down to all the way.
Yeah.
Right. And it's minus infinity on that whole
Okay,
line.
good. Now I have the picture correct, right? Okay, so the function is 0. The derivative here is 0 minus infinity and 0. Here is 0 minus infinity and 0. So if you're here and you still...
You first just look at the horizontal derivative. So it's
No, this is the horizontal derivative. So if you're here, my
yeah,
claim
so
is
it
that...
goes from, right, so it's 0 minus infinity 0, and then above
So-
that it's only 0.
Oh, I see. Sorry. It's 0 all the time out here.
Yeah.
Yeah, and it's 0 all the time out here. And the only case when the sign is minus infinity, and eventually from minus infinity you can only move outside the set, in which case you're 0 as well. I just drew the set in a horrible way. Okay. Does it make sense, Claire? Okay. So yeah. Sorry. I messed it up when I was preparing, and then I messed it up backwards. But yes. So the derivative is minus infinity here. If you're not on the boundary, then it's just 0 all the time as you move. I mean infinitesimally. And if you're on the boundary, obviously you can only go up from minus infinity. It's a bit, yeah. Okay.
The first derivatives are negative.
They're non-positive. Yeah. Yeah. I mean, as you because they're. I mean, that's why we chose them half spaces to the left. I mean, you can only be as you move in the positive direction, you can only move out of the set. You know, if we had chosen them the other way, which is what I did, now I realize initially, then everything switches. Okay. Okay. But yeah. Okay. So you do this, and then you switch again, right, to the complement, and you get that the probability that this thing is big is less than the probability this thing is big. Okay, and then this follows. I mean, everybody's very agree that this line goes to this line. I mean, you can use like you can, if you want, you can. You can write it like this. You can write expectation like this and see that all these things give you that point-wise, these for the x's are bigger than for the y's, and these for the x's are smaller than for the y's. Okay. So we get this sort of, so we get this I don't want to call it majoration, but so we get to the fact that the expected supes of the x's are bigger than the expected supes of the y's. Okay, so we've proven that sort of as the distances decrease, the expected supremum of the process goes up, and therefore we can always reduce to the independent case. Okay, so I have 5 minutes. I want to at least finish this stuff about Gaussian processes so that the next time we can actually finish the proof of the majorizing measures theorem. We need something slightly, it's okay that I erased pseudo-Gaussian inequality. We need something slightly stronger than pseudo-Gaussian inequality, which are right here, which is the following idea. So again, we have a Gaussian process. And then hopefully we'll be able to see where the final lecture is going at the end. Again, we have a Gaussian process. And now suppose we take a bunch of points, which are all in T, and Ti, Tj is bigger than or equal to alpha. So far, okay. So far it's in the same setup as before. But now I want to get a slightly stronger inequality, which is the following. I want to say that the expected supremum of this. So basically, what we did was pseudo-Gaussian inequality picked up one scale. So if we know that these points are uniformly separated, we get some lower bound. But if we're going to build this tree, then we need to pick up this scale plus the rest of the scales that are coming from smaller distances. Okay. So here's the inequality that we're going to want to use. We get alpha square root log m, like before, but we're also going to get the following: the minimum of the expected sup. But now, so let me write it, and then we'll prove it. I mean, then I'll explain what's going on at least. Okay. So here's what's going on, and it's best to draw a picture. So we have t, and we have all these points t1, t2, t3, t4, and so on that are separated. We know that since there are so many of them and they're all at least alpha apart, that the expected supremum is going to be at least this much. But now we'd also like to get, we put these small balls, these balls of radius alpha over c. C is some constant I haven't specified yet. Okay, so these balls are radius alpha over c. What we're saying is we'd like to get the contribution from these centers ti, and then also this minimum is over all these balls. And then also we'd at least like to get the contribution of the expected supremum from the smallest ball here. Okay? So what we're saying is, look, we know we're going to get, like, let's fix some center t0. We know we're going to get some large, like we have all these experiments. From the Sudokov inequality, we know that one of these is going to be large. I don't know which one it's going to be, right? I can't control that. One of them will be large. But then I should say, okay, well, if one of these is large, then I should at least be able to get a little bit more, or maybe possibly a lot more, from the expected supremum over this ball as well. So I want to be a little bit greedy. I want to get not this, but this plus whatever the expected supremum in this ball is as 2. So this some kind of inequality like this. Yeah. So well then I mean that's going to be the hard part. We do that next time, which is going to be somehow we need to choose this tree of balls in a very clever way so that we can never lose anything more than a constant factor in constructing these trees. So we need to choose them very cleverly. Let me just mention how this is proved so that we have this inequality up for next time. So let's prove this, and then the next time we'll discuss how to actually use it to construct these trees. But yeah, I mean, this indicates that we're going to prove a lower bound by some kind of iterative process. We find these balls that are well separated. We get this contribution now, and then we get a contribution. Then we get to go inside one of the balls and get the contribution there. Of course, inside the next ball, we're also going to do something similar and keep recursing. But the reason it's hard is because we only get the minimum. We don't get to choose which one of these values is going to be large. We only get the minimum one. So when we choose the balls, we have to choose it so that they're as balanced as possible. It does us no good to have a bunch of sort of supremum in this ball and have a tiny bit in this ball, because then the process could say, well, okay, well this was large, and now I don't get any credit for that. So there's got to be some kind of balancing that goes on when you choose these balls. But let's just let's look at how you prove this. Okay, and the basic idea is as follows. So I mean, we want to take a union bound. We like to say that, okay, how could you prove this? One way is say, look, the probability that any of these balls is much smaller than its expectation. Like take a union bound over all these balls. Say all these balls are close to their expectation, and then we'd be in good shape. Sort of like if they're all simultaneously close to their expectation, then we don't even have to condition. We just sort of like, we get this this will come for free. So the whole goal is to show that sort of the supremum in each one of these balls, we can take them all simultaneously to be close to their expectation. Right? So we're just going to we're going to say, at least, first of all, one of these balls is close to its expectation, and then all simultaneously. And the problem with doing that is you can just look at one ball. If we look at the process restricted to this ball, look at this value. Why should this value be concentrated? I mean, we have no idea what the configuration of the process is inside here. In particular, there could be, we don't know how many points are inside here, so we can't take a union bound over all the points in this ball. So we use the following fact. This fact, by the way, is probably the thing that makes majorizing measures the most specialized to Gaussians. So it's the following concentration fact. So it's a classical theorem, but here's the fact. The probability. So let's just take any. Okay, let's again take any process. Then the probability that the sup of this process minus the expectation of this process of the sup, the probability that this is bigger than some lambda, is at most, and here's the factor which is very special to Gaussian, e to the minus lambda squared over something. And here's the thing which is nice. Here we can actually put the maximum variance. So the best. So we can put the soup of xt squared. Okay, so the soup is concentrated around its expectation in a way that doesn't depend on the size of the set capital T at all. It only depends on the maximum variance there. In the language over here, the maximum variance in this ball is basically is proportional to the diameter. So the maximum variance here is like, I mean, the diameter is twice alpha over c. Okay? So what it means is that since these balls are small in the metric space, their values are going to be very concentrated, and in fact are only going to differ they're only going to differ from their expectation by this much, say. Okay? But we're adding on a term here that's like really huge compared to this. So somehow the fluctuation here is not too bad, even if we take a union bound. So now we have m balls. Suppose we use this and take a union bound. Then the fluctuation of the worst one could be like this. But if we choose c to be large enough, this is still tiny compared to this. So basically, we can use this inequality, take a union bound over all the balls, and get that the value in each one of those only fluctuates by this much. Okay? But we're getting this much from this level. So if we choose c to be large enough, choose c to be 100, this is negligible compared to this. And the fluctuations don't mess up this term. Okay, so we get their expectation, possibly minus this fluctuation, but this fluctuation can be swallowed up in the main term. Okay, so let me just, let's do it in 1 minute. How do you prove this theorem? So you prove this theorem from this classical fact that if we take any function from Rn to R, okay, so and equip here. Let's equip this with the Gaussian measure. I'm just writing down the Gaussian isometric inequality. Then the probability that f of x1 up to xn minus the expected value of f x1 up to xn is bigger than lambda is at most e to the minus lambda squared over something that depends on the Lipschitz constant of f. Okay, so this is the classical fact. It's not so. If you want to prove it without the optimal constant here, actually, you can do it in a page or two. But this is a classical isometric inequality in Gaussian space. That if we take any function on Rn equipped to the Gaussian measure that's Lipschitz, then the function has to be tightly concentrated around its expectation.
But even this is not like particular for Gaussian.
You're right. This is not particular for Gaussian. So how do we use it to prove this? Okay, so that's the last step. Like, what f do we use it for? So this is the fact that's going to be. You're right. Even.
Oh, you're not taking f, which is just the superman?
No. So I mean, the superman is Lipschitz, but we need to. What's the issue? Why is there something confusing here? I agree. The supremum is Lipschitz. The supremum is in fact 1 Lipschitz. So there's something tricky here. What's the difficulty?
You're missing in this inequality some estimate on the second moment of that.
Nope. No, this is trivial to prove.
Why would you need anything other than, why can't you just take f to be the supreme?
First of all, I mean, I can give you a trivial reason that like this gets better if you take the variance as going to 0, and this wouldn't. So, but that's not very convincing. So the question is, why can't you take f just to be the?
That's because you're using the 2 norm here, and the supreme is Lipschitz in the infinity norm.
I agree, but
that's so it gives you that result, which is
no. You want to claim that it gives you this result, but I disagree. So you need to see why I disagree with you.
How about recapping this?
Okay. So anyway, from this inequality, we saw that you can sort of like you can prove this, and basically what we're going to do next time is somehow choose this tree very carefully so that applying this inequality at every level gives us something that meets the expected maxima to a constant factor. So we'll stop now, and if anybody's, this will be resolved in a second if anybody's truly interested. So what's the problem here?
So